Okay. Hi everyone. Welcome back to the video lecture series. So diffusion in solids. We are continuing. In this one, we are considering the new topic called as random walk theory. To calculate the mean square displacement of an mean square displacement of an moving atoms. Okay. So first of all, getting into the topic, this topic consisting of two concepts, that is random walk and mean square displacement. So first, what do you mean by random walk? That means, in general, I will explain the concept. Consider this is an atom. Okay, it will move in a space from here to here. Again, due to some obstacles, it will move from here to here. Again, from here, it will move from here to here. Finally, it will reach us to, and it will get stabilized here. It is traveled from path 1 to path along the path 1, 2, 3, 4, 5 respectively. But the displacement is this much. Okay. So this is the random walk. A person moving randomly. Consider a person moving aimlessly. Similarly, here the atom will move aimlessly. If is there any obstacles, it will reach to and it will take another direction. This is kind of a good example for the random walk, and it can be measured R star as a indication R1 plus R2 plus R3 so on plus Rn square Rn bar. This sum of the total random walk of a component is given as the random walk of an individual atoms. For example, consider this is a box consisting of some 4 to 5 atoms. Okay, it is moving from here to this direction. So we need to consider the random walk of a whole component, whole system is sum of the random walk of an individual component. It is given by small r. The whole system random walk is given by r bar. Okay, so now we can define the random walk definition. Random walk of a particle, we are considering a particle A here, does not depend upon the previous jumps and its magnitude and its directions. R bar. Here I will write these sentences. It's very important. A random walk particle does not depends on depends on previous jump. Previous jump, its magnitude, and direction. Okay, this is direction is given by r bar, r dash. Okay, so we used to consider there are large number of particles. We used to consider the average net displacement of all atoms. This is a displacement of an atom, and we are averaging. We are taking the average of those displacement. This is given by average of net displacement. Displacement of all atom. For true random walk, this is very crucial statement. What I am mentioning here is, for a true random walk, the average displacement is equals to 0. Okay, this is a statement. How it is 0? I am giving a justification for this statement right now. Okay, consider an atom with a net displacement of Ri. Consider atom with net displacement of Ri, then there is a another probability that atom is present opposite to Ri, that is Rj. So it is different notation. This is different atom with the same magnitude. But opposite direction. Hence, there is a cancel of atom with each other. I will write here with each other than. That's why average means per average is 0. So here the white screen I can explain. So consider the atoms randomly moving. Okay, this is a system. Okay, these are the atoms which are moving, and we are measuring the distance of a single atom, that is Ri distance from a one point. Okay, this is the direction and the magnitude. This is the magnitude and direction of the this atom, moving atom. But in random walk, there is a probability that may be another atom opposite to this one with the same magnitude R only, but a different direction. That means opposite direction. So this atom will pulls towards this side and this atom will pulls this side. Hence, it will cancel with each other. Then the average net displacement is 0. This is like pulling of a rope. A person is pulling a rope, and here the another person is pulling another a rope with the another side, but they are having the energies. They are applying the forces in the same forces they are applying, but in a opposite direction. That's why the pulley, so rope, will remains in its position forever. That's why the movement of this rope is 0, considered to be as a 0. That's why the average net displacement is 0 in the random walk. This is the meaning of the statement. Hence, we are not considering the average displacement in the random walk concept. That's why we are moving towards the mean square displacement. Zero. We are not considering average net displacement. But usually the atom will move from one place to another place, and there will be a diffusion due to the movement of these atoms. So this concept will fail. We are not considering because average net displacement is displacement of an atom in a random walk is 0. Okay, but which is actually it's not true, which is not true. Hence, we are considering a mean square displacement. Okay, So what is mean square displacement? So it can be denoted with the help of R square. Mean square displacement. This is a mean value and this is square. Hence it is denoted by like this. Okay. So mean square displacement so this can be denoted as average square of net displacement. Average of square of net displacement of all atoms. Okay, so let's derive for there is an expression for this one. I will write the first expression, then I will derive this one. Okay, that's the best way. R square is given as summation of I equal to 1 to n Ri square plus 2 into I equal to 1 to n minus 1, j is equals to I plus 1 up to n Ri bar Rj. Okay, so this Ri and Rj are the magnitudes of ith and jth jump factor. This is the final equation, which is very important. Now we will start to derive. R square is equals to R bar. So from the previous slide we are know values of R1